I want to introduce to you Professor Jena. He's got 35 years of experience in imaging and computer science, and he's been teaching image processing at Heidelberg University since 1994. He is a board member of the EMBA and is a chair of a number of very important committees and groups, including the EMBA 12888 Standardization Working Group. He is also author of a book, Digital Image Processing and Image Formation, and has been released in multiple languages. His commitment to image processing and furthering the community is very, very strong. And we're really glad to have him here today to talk to you a little bit more. Welcome, Professor Jena.
Yeah, welcome to all of you. It is really a great pleasure to be here at this summit, and it's an honor for me to give the keynote, how to build basically an optimized imaging system. In the half hour I have for that, of course, it is only, I can only touch some things. So I decided basically to divide my talk into two topics. One is just to give you an idea. If you just know a little bit of the fundamentals of imaging, you can already make some really good and intelligent choices about the best system for your application. And second point is what was already pointed out by Greg as well, is of course that we take a look ahead, how are going imaging systems to change in the future. And this will be the two things I would like to cover in my talk. It is actually, I just have to check for that the system gets to the next slide. Now here we are. So let's go to the fundamentals first of optical sensor combinations. And Greg mentioned already that I'm quite long in this business. Actually, I started with the PhD, which was in 1977. And that time I basically Edmund Optics accompanied my research. So it's really funny now to be at the end of my career here and still being involved with Edmund. So fundamentals about optical lens sensor combinations. So imaging system, as you all know, consists of a lens and a camera. And the question is, how is the optimum combination of that? And the first thing, of course, what you want to have is the first requirement is you really want to have good image quality. The picture should be sharp and it should be not noisy as it is here on the right image. And so the first question we have to address is what actually determines the level of noise in an image. And to get a feeling of that, I started here a first survey, which Boris Lange was already mentioning, about the question on which parameter does the signal to noise ratio of a modern image sensor really depend on. And I have 4 answers for you here, which you can select. The first is, is it the temporal dark noise of the image sensor? Then the other question, the answer would be, is it actually the power received per area, which you can express either in watts per square meter or in photons per square meter, and second at the image plane? Or instead of the power per area, is it rather the power received by a single pixel of the image sensor? Or even another variant, is it not the power, but the radiant energy received by a pixel of the image sensor? So think for a moment, what is the right answer? And we wait for a few seconds here to give you the opportunity to answer this question. And this will help us and guide us then finding the correct answer, which I will present in a moment then. Now, please use the opportunity to decide which of these 4 possible answers might be correct. So Boris Lange is watching the answers coming in, and he will decide when to show the result. And it's interesting to see that we have quite distributed answer. So obviously, different the different people here think about different. And actually, the most interesting thing is that the correct answer gets the least votes here. Actually, the correct answer is really the radiant energy received by a single picture is with modern image sensors the decisive thing. And now let's think about why is this the case. And I switch to the next slide here. Also, first I have to activate the screen again. So how does basically a camera which converts photon into a digital signal work? And the nice thing is I can show this to you actually without any equations. You have a number of photons which are basically hitting the pixel area during the exposure time. So you can already see, obviously it's integrated over the exposure time. Then the photons are converted into charge units and are collected. This forms basically something like a capacitor, and the voltage of the capacitor is proportional to the number of charge units. This is being amplified, digitized, and finally you end up with a digital value in your camera. And if you look now how this looks with equations, well, then you can simply see it's going this way. You take the irradiance, which is the number of photons per second and per square meter. Since it's per area, you have to first multiply it with the area of the pixel. And since the pixel integrates over the exposure time, then you have to multiply it with the exposure time. And this gives you then the whole energy received by the pixel. And to get the number of photons, all you have to do is divide this figure here by the number of, by the energy of a single photon. And the energy of a single photon is given by the famous Einstein relation, which is written here as Planck constant times speed of light divided by the wavelengths and not the frequency, because we are more used to think in wavelengths. And this can be converted in units, but the essential thing now is what we are doing is we are basically collecting photons, and these are converted into electrons. And so the signal to noise ratio is now signal divided by the standard deviation. And since we are not counting the photons themselves, but only the electrons, which are less, and this is a famous quantum efficiency. So the number of electrons which are counted is number of photons times the quantum efficiency. And this is a so-called Poisson process. And so you'd have the standard deviation is actually the square root out of this figure. And so we end up basically that the signal to noise ratio, which is a true measure for the quality, is always the question not how bright the image is, but what is the relation between the signal I'm interested in and the noise, temporal noise, which is in the signal. And so you see, the more electrons we collect, the higher the signal is. And since this is just then the energy received, you can easily see that answer 4 is correct in this case. And just to show you the signal to noise ratio here as a measure, maybe I go back again to explain this is a square root relation. And if a square root relation is shown basically in a double logarithmic plot, you have a slope 1/2. The black line here is actually the best possible sensor with no dark noise and also a quantum efficiency of 1. And since the quantum efficiency is a little bit lower, you get a little bit worse signal to noise ratio, because not every photon is converted into an electron. But then the curve is parallel for a wide range of intensities, and dark noise, which many of you said is decisive. Well, this is only important if it's very, very low intensity. But for the most range, which is for most applications of importance, it is basically the more photons we get per pixel or electrons we can capture, the better the signal is. So that was the first question. But now the next question, and we come now from the camera to the lens, is how much actually irradiance do we get at the image plane? And what parameter of the lens basically determines this. So the question now with the second survey is the radiance at the image plane depends on what parameter? Well, you might think if I have a lens with a big entrance pupil at the diameter of the aperture, then I get a lot of light. And so the diameter of the lens aperture is what is really decides how bright an image gets at the image plane. Then you might think, oh, it might also depend on the f number of the lens. Or you might think, well, it could also be the focal length of the lens. So 3 options you have here to decide about. And I'm now really curious to learn about the distribution of the answers, and then I'm going to explain what is correct. So let's wait for a short while. Wow, that was really quick now. You get used to interactive the interactive nature of this presentation. That's perfect. A steep learning curve here. And here I also see clearly that most of you actually gave the right number. It is not actually the diameter of the entrance pupil. It is really the f number. And let's see how this is expressed now in equations again. And so I show you here the theoretical relation of what's called the radiometry of imaging. So we have a certain brightness of an object, which is expressed with a radiance, watt per steradian and square meters, what an object is distributing into the space per angle. And then we have the irradiance at the image plane. And then I have marked in red the most important parameters. And actually you see here really the f number and not the opening of the lens. The more you close the lens, the larger the f number is and the less light you receive. And it's going with a square because it's actually not the diameter, but the area you are receiving. And this is why it's a square here. But you see one interesting deviation we have not yet considered. There is also a dependency on the magnification factor. And the reason for that is, and this will be shown in the demonstrations later, if you want to have, let's say, a macro imaging, or let's for simplicity take a one-to-one imaging, then the lateral magnification is basically 1. And then you will see, according to this equation, we have only a quarter of the light. And this has to do with that you shift the whole image plane just by 1 focal length further away. And since it's a double distance, it's only a quarter of the intensity you get. So macro imaging, and especially micro imaging with microscopes, you need a lot of more light to get a certain irradiance at the imaging. For the normal kind of things where the lateral magnification is small, you can forget that, and it's then only the f number. So independent what focal length you choose, it's only the f number which defines how much irradiance you get at the image plane. The next requirement, which is a decisive thing for real applications, is that the imaging equations tell you, well, only at a certain distance you get a really sharp image. If it's a little bit further away or a little bit closer, basically the unsharpness increases with the distance to the focused plane. And again, we have the interesting question, what determines actually the depth of field? Because you want to know, does the optical setup camera plus lens really cover the depth of field you need for your application? And so I am asking the question again, on what does the depth of field depend on? Is it again just the same possible answers? Is it again the diameter of the lens aperture? Is it the f number, or is it the focal length? So again, I ask you for your answers. Check what is the right thing for the depth of field. And I'm now really curious about the answers again. Takes a little bit longer. Okay, again, a little bit more distributed opinion, but interestingly, again, obviously, you are more familiar with lenses than with image sensors. It's clear the right answer, namely that it depends only on the F number, got the most votes. So let's then look why this is basically the case and go to the next slide to explain you. So what is a depth of field? Well, we have the sharp object plane here at this black dot, and this corresponds to a sharp point here at the image plane. And once we go a little bit further away and a little bit closer, you see you get a certain blur disk, and you can now allow a certain blur disk, which is for sure in the order of a pixel size, which you can allow so that you still get a kind of a sharp impression for a certain depth range. That is how you can define that. Now you can easily see the further I open up, of course, the aperture here, the larger the blur disks get. But again, it's if you change let's say the focal length, you get twice as large. Then you also have to make the opening twice as large to get the same blur disk. And so, not surprisingly, the depth of field is again just determined by the F number. So the F number is really a very important issue of a lens, and this is why this is also written on the lens, and the lenses are characterized by the F number. But wait a minute, here actually the magnification now is much more important. Again, if we assume that the magnification is small, so normal imaging, then actually the depth of field increases with the magnitude squared inversely. So it's really a big effect. If you have your object 2 times far away, which means the magnification factor is about 2 times smaller, then actually the depth of field increases by a factor of 4. So it's actually not the F number. So often there is a misconception that if you have a Taylor lens, this has less depth of field than a wide angle lens, but that's not true. It's only determined by the magnification factor. This is what the crucial thing you have to think about. So the question we have now to answer, because the magnification factor depends also on the pixel size. Imagine you are imaging the same size of an object and you get it to smaller pixels. Then the magnification factor is changing. And so the question is now, what are the advantages and disadvantages basically of small pixels? First thing, of course, which may immediately pop up in your mind is that, of course, you have a big cost advantage if you go to smaller pixels, because you have much less expensive image sensors. Also, the lenses are smaller, so you save also with the lenses. But remember, the question is how much basically light could be received by a pixel, and the signal to noise ratio, if you remember this equation, I have just rewritten it here now in all the decisive terms with the irradiance, which is constant. That depends with the same F number, we have the same irradiance at the image plane, but then it's proportional basically to the exposure time and the area, and the exposure time is typically given by an application or by the camera you use. The irradiance is given by the illumination and the whole setup of your system. So the essential point is basically the area of a pixel. If the area of a pixel is larger, you get a higher signal to noise ratio. So imagine your pixel size is twice as large, the area is 4 times larger, and since it's again a square root, the signal to noise ratio is 2 times better. So that means basically the SNR scales directly basically with the diameter of a pixel. So that is a disadvantage if you go to smaller pixels. You get more and more, less and less signal to noise ratio. But what you get at the same time, if you choose to reduce your pixels to half the size, then either you can think about magnification factor or you can think about basically the pixel size. the depth of field basically doubles if you go to a pixel only half the size. That is an important issue. So you can increase the depth of field by going to smaller pixels. Yeah, and you can easily see by this, if you have such a little bit knowledge about the basic physics which is behind the imaging, this gives you really a precise and reliable guidance what to choose for your application. Your application, of course, depending on the image processing you might be rather tolerant to the signal to noise ratio or depend very critical. So you have to choose between these two things here. So let's still look now for another issue in the same relation, that's the curse of high resolution as I name it here. And it's about the question of the disadvantage of the high resolution. There's a typo here, sorry, that should read as the question of high resolution. If you go to more resolution, you need a sensor with more pixels. Of course, that is a little bit more expensive, and the same is true for the lenses. Again, there is the cost question. But let's look again for the lower depths of field, what we get. I have written it again here in two different, that's the same equation, now only focusing basically on the resolution. Resolution is now in object space, so what type of resolution do we want to get? Can immediately see if you shrink the pixels, that means you take now a sensor, same size, but half size of pixels, then the depth of a field is basically shrinked by a factor of 2. Whereas if you say, well, I want to have the same signal to noise ratio and I double the size of my sensor, then the depth of field even decreases with the square of your resolution. So you get 4 times less depth of field. That is, of course, not a problem if you have a planar object, but if your application needs different distances, be very careful with high resolution. So again, there is also, of course, this trade-off between depth of field and SNR. And a general rule I can easily express here is choose only as much resolution as you really need. There would be much more to be said, but there is no time for that to be done. So the next thing what you want to have is, of course, you don't want to have no artifacts in your image. And this can be nicely demonstrated if you look for certain patterns. This is now, I have chosen now a lens with infinite resolution, and I get then this perfect image of these finer and finer structures until the very finest you have here at the edge. Now, if you integrate now this signal, assume we have a certain pixel of a certain size and we integrate the whole signal over it, then you can see even with small pixels, you start seeing some artifacts here. And if you increase the pixel size, that gets really worse. You simply see wrong structures. You have probably all seen that. It's called aliasing or moire effects. And the story is that basically, as you can see by this simulation here, the image sensor is really a very bad bandpass filter. The image sensor is, for those who are familiar with image processing, an image sensor is as bad as a box filter. So the image sensor cannot do a band limitation. And with that, we immediately know that just taking the sharpest possible lens you can buy is not the best solution, but you have to adapt your lens in an optimum way to the pixel size. The optimization criterion will depend on what patterns you actually have to analyze. If you have especially these periodic patterns, it's very critical. If you only have edges, it is less critical. Object with constant size and only edges, it's almost not critical at all. And interesting observation is actually if you have a diffraction limited lens, then this is in some sense optimal because it produces over the whole image a homogeneous sharpness. And the lens actually, in contrast to the image sensor, is a perfect bandpass filter. You will probably learn that also in the future demonstrations today. So at the end, I promise you what is going to change in the future, and it is not less than that the limits of traditional imaging will be overcome in the near future. And we have seen already this trade-off between the depth of field and the pixel size, or the aperture we are using. You can of course always get a large depth of range if you close your lens down, but then you have not enough light, possibly. And so the big question is, can you have something like what is shown here? You see, this is a narrow depth of field focused to a far distance, here to a close distance, and here that is now what we wish to have. Let's have the lens open the same way, but get a extended depth of field here as it's shown here. And this can be done, interestingly, if you design a bad lens. So normally you think about, let's have a good lens, which makes a perfectly sharp image. But the idea here is, let's take a lens which basically has a bad chromatic aberration, a so-called hyperchromatic lens, which basically focus the blue, the green, and the red to different distances. Then you have the different color channels of your image sensor sharp at different things, and all you have to do is you have basically to transfer this sharpness to the other color channels, and this can be done quite nicely. You see here the hand, which is very close, and the object here very far away. Both are sharp with these things. I see it also here. Here you see actually some nice aliasing effects here in this small image. You can even make basically a coarse depth map with this simple trick. This technique is called so-called extended depth of field. So the advantage is you can leave your lens open, but get a much larger depth of field. And the common thing behind it is what's called computational imaging. And this will enable in the near future a whole new generations basically of vision systems. You deviate from the traditional approach. The traditional approach is, here I have my lens, here I have my camera, I try to make a perfect lens, well adapted basically to the pixel size, of course, and then I have a camera which takes the whole thing. Computational imaging says we have to consider the whole system and optimize the whole system. And it's a kind of a synergistic approach which includes the optics and the image processing to overcome these limits of traditional image acquisition systems. So I showed you already this increase of depth of field, which is called extended depth of field without closing the aperture and having less light. That is only one of the many techniques you can do. You can do a very similar trick, which is again not very well known at the moment in the community. All of those who have to observe fast moving objects know about the problem. You have basically to reduce the exposure time. That means you get less irradiance at the image plane, and you have really troubles. Then you need a lot of illumination to get enough light for fast moving things. But there are also techniques in the same way. What you can do is you can reduce the motion blur without reducing the exposure time again with some interesting tricks. In the same way, you can start thinking about, well, what determines my resolution? We have seen it's basically, of course, the image sensor. The lens could be better. And there are actually also techniques to do super resolution, several tricks with additional image processing to increase the resolution beyond the limit given by the resolution of the image sensor. And in general, you can think about, of course, getting really intelligent acquisition systems where actually the camera, where more and more processing is taking place. Remember, we are entering the age of embedded vision. So more and more processing is going on really in the camera. So you have the options. And imagine now that your imaging, your camera knows about the lens data, the illumination and whatever. Then you can make actually a system which by itself is intelligent enough to select the optimum combination of aperture, exposure time, and whatever and even noise level in the image. because you have all these systems at hand. That's actually something which you experience in the moment already in the consumer market. Many of the both high-end cameras, but also every camera you have in a mobile device uses already a lot of tricks to do that automatically in the best possible way, but something which has not yet entered machine vision too much. However, we have a problem with this approach. We really need to know more about the lenses to do this kind of things. And that means we need to have established a communication between the lens and the camera. And if you look now how the machine vision lenses look like, well, they are all dumb. It's just mechanical connection. You remember, I've shown you here a number of cameras with the famous C-mount. You just can screw in your lens and that is it. No kind of communication. Actually, it's funny to see this dates back to 1929. The C-mount has never changed since that. And even if you use now larger image sensors where you use mounts from system cameras, M42 or Nikon F are the most common ones, you use them basically typically without an electrical interface, which is already there. So, and if you look now in the consumer world, it's also not a real nice story because the lens mounts of commercial system cameras is, just to say it in one word, is a mess, because almost each manufacturer has its own bayonet, its own communication protocol. Also, the bayonets are actually not really very good for machine vision. They have too much play for many mechanical play for many machine vision tasks. And you have really a hard time to do a reverse engineering of the proprietary interfaces. Some companies are out there which do that. So what is really urgently needed is basically a new standard, and that's the solution. That's one thing which EMVA has recently started, an open optics camera interface, in short OOCI. And this is based on something, for those of you who are working also with cameras, know it very well. It's a GenICam, which is basically a generic interface for cameras to computers. So without whether you have USB or GigE or CoaXPress or whatsoever, you have the same basically software interface. And into that, we found out it's quite easy to integrate now also the features of optical components, like focus, focal length, aperture, shutter, filters, stabilization, additional axes such as camera, pan and tilt, or whatever you might think of. The nice thing with these approaches, which is common to GenICam as well, is that proprietary features can be added. We have started discussing this new interface for support of multiple optical components, for instance, a lens plus a tunable filter, or a liquid lens within a lens, which you can use. And we are thinking about various types of standardized electrical interfaces now between the lenses and the camera, and possibly, of course, then also new optical mounts. So with this, I would like to conclude my talk. Just you might feel, oh, you have addressed so many interesting things. Where can I learn more? This is one of the tasks which EMVA is also doing. So especially if you want to learn more about to choose the best camera for your application, then the EMVA standard 1288 is very of interest. There are 4 free webinars, for instance, available, and there is also a detailed education available for those who really want to do the measurements themselves. And you will receive then with the slides with Edmund is sending you all these links which you can just click on and then get additional information. And I'm very pleased, especially about the very last thing which is here on this slide, is that Edmund and also EMVA have decided to offer a one-day technical course online again, technical optics for machine vision, where we can have that all in detail on one day. It's a one-day online course, and we are preparing that in the moment, and it will take place at November 24. this year. The details will be announced soon. So watch either EMBA pages or a web page or Edmund, and then you will see that there is an opportunity to learn much more about that. With that, I would like to thank you very much for your attention. You will also have more slides here which show you more, just more links to further information, but there's no need to show it here. So thank you very much again for your attention, and I look forward to questions and the further proceeding of this very interesting Innovation Imaging Summit of Edmund.
Thank you very much, Professor Jena. It was very enjoyable, and you went over a variety of topics that just show how important it is to select the right components and get your system built correctly.